Albert Einstein, a name synonymous with genius, changed the way we understand the universe with his theory of general relativity. It described gravity not as a force, but as the curvature of spacetime itself. This revolutionary concept led to the idea of singularities, regions in spacetime where matter and energy are impossibly concentrated. These enigmatic points of extreme density are believed to occur at the birth of the universe in the Big Bang, and at the heart of the most mysterious objects in the cosmos, black holes. But here's where it gets truly fascinating. These singularities, these points of infinite density, they raise puzzling questions. Questions that challenge our understanding of the universe and its origins. And these questions have ignited a quest for answers, leading scientists to theories and concepts that stretch our imagination. From cosmic inflation, an early phase of the universe before the hot Big Bang, to the possibility of new universes being born within black holes. But the most captivating part of all this. Now that's a story for a little later. Stay with us. What's up, my amazing and curious folks? Ready to unravel some mysteries together? I'm your host, Caesar, and with me is the insightful Sonia, ready to dive deep into the mysteries of the universe.
Hi everyone. Excited to be here.
And remember, if you want to keep up with us and your daily dose of curiosity, subscribe to our channel and hit that bell icon. You won't want to miss out. Shifting gears slightly, let's delve a little deeper into the concept of singularities. As Patreon supporter Cameron Sowards astutely asks, why do we believe that the pre-Big Bang state was not a singularity when it is a much higher concentration of energy than a black hole could possibly have? Since the pre-Big Bang universe was not a singularity, could the same mechanisms that prevented it from being a singularity apply to the interior of black holes? Quite a mouthful, isn't it?
It sure is.
Well, to unpack this, we need to understand a bit about the nature of black holes and the Big Bang. See, once you cross the threshold to form a black hole, everything inside the event horizon crunches down to a singularity that is, at most, one-dimensional. In simpler terms, it becomes a point of extreme density, a point so dense, no three-dimensional structures can survive intact.
That's mind-boggling.
Yes, and intriguingly, a coordinate transformation shows that every point in the interior of the black hole maps one-to-one with a point on the outside. This opens up the possibility that the interior of each black hole could potentially give rise to a new universe, a baby universe, if you will. This leads us to the question, could our universe have arisen from a black hole in a pre-existing universe?
And the plot thickens.
Indeed. When we look at the Big Bang and question the existence of a first singularity, things get even more interesting. If we start with the basic observation of our universe being full of matter and energy and then factor in that it's expanding today, it might lead one to conclude that there must have been an initial singularity almost 100 years ago, back in the 1920s. But, the pre-Big Bang state being a singularity, and whether the same mechanisms could prevent it from being so, well, we'll get to that soon enough. Now, when we observe our universe, we see that it's roughly the same in all locations and in all directions. This uniformity is what astrophysicists call homogeneous and isotropic. Essentially, no matter where you are in the universe or which way you look, things look pretty much the same.
So, it's like every part of the universe is a mirror image of every other part.
Precisely, and this uniformity leads us to the Friedmann-Lemaitre-Robertson-Walker metric, or FLRW for short. This metric describes the spacetime of the universe and its relationship to the matter and energy within it.
So, the FLRW metric means that the universe can't just stand still, it has to either expand or contract?
Yes, that's correct. Observations of distant galaxies show that their recession speed, or redshift, is directly proportional to their distance from us. This tells us the universe is expanding.
And if the universe is expanding now, that means it was smaller, denser, and hotter in the past, right?
Absolutely. And if we extrapolate backwards, the universe gets smaller and smaller. If we go all the way back to the start, when its size was 0, we arrive at what we call a singularity.
Can you explain how the concept of redshift fits into this?
Well, as the universe expands, light from distant galaxies gets stretched into longer wavelengths, which we interpret as a shift towards the red end of the spectrum, hence the term redshift.
Okay, so redshift is basically a clue that the universe is expanding, and this expansion implies that the universe used to be smaller with all its matter and energy concentrated in a denser state. That makes sense.
Exactly. And this concept has held sway for most of the 20th century, backed by key observations that align with the Big Bang Theory. Now, there are 4 key observations that back the hot Big Bang Theory. First, the universe is expanding, which we've already covered. Second, the cosmic structure of the universe has evolved from a roughly uniform state to a complex structure of stars, galaxies, and clusters. Third, there's a cosmic microwave background, a kind of leftover radiation from the hot Big Bang, when the universe was still too hot for atoms to form. And finally, the abundance of the lightest elements and isotopes, including hydrogen, helium, and lithium, all forged during the hot Big Bang before any stars could form.
Could you give an example to help us understand the cosmic microwave background?
Sure. Imagine you've just baked a loaf of bread. Initially, it's too hot to touch. But as it cools, it releases heat. Now, imagine our universe as that loaf of bread. The cosmic microwave background is like that heat being released as the universe cooled.
Fascinating. And what about the abundance of the lightest elements?
Think of it like this: in the intense heat of the Big Bang's oven, only the simplest ingredients, or light elements, could form. Heavier elements didn't come into the picture until much later, in the hearts of stars.
That makes sense, but this picture of the hot Big Bang has some unresolved puzzles, hasn't it?
Indeed. For instance, there are no high-energy relics from the epochs of incredibly high temperatures, which is a bit like finding no charred remnants in a house that was supposedly on fire. This is known as the monopole problem.
Right. And what about the other puzzles?
Well, we also have the so-called flatness problem, which deals with the perfect balance between the universe's expansion rate and its total energy density. It's like flipping a coin and it landing perfectly on its edge, not heads or tails. And then we have the horizon problem, which questions why different regions of the sky that haven't had time to exchange information appear to be in perfect thermal equilibrium. It's like two people who've never met having the exact same dream.
Well, those are some huge mysteries. I guess there's still much to learn about our universe.
Despite the unanswered questions of the hot Big Bang Theory, there is a mechanism that could answer these, known as cosmological inflation. This theory, proposed in 1980, suggests that there was an early phase to the universe that preceded the hot Big Bang.
Interesting. So, does this cosmological inflation resolve the problems we discussed earlier?
It does indeed. It provides explanations for the absence of high-energy relics, the perfect balance of the universe's expansion rate and energy density, and the thermal equilibrium across different regions of the sky.
Does it also make predictions?
Absolutely. It predicts quantum fluctuations stretched across the universe during cosmic inflation, giving rise to density fluctuations in the cosmic microwave background, which eventually led to the formation of stars, galaxies, and other large-scale structures.
That's fascinating. But, does this mean the universe started with a singularity?
That's where things become murky. If the universe is dominated by vacuum energy, as it is during cosmic inflation, tracing it back doesn't lead to a singularity. It leads to a progressively smaller but still finite and non-zero size.
So, are we saying that inflation wasn't the first chapter of our universe's story?
It's a possibility. The jury is still out regarding whether something existed before cosmic inflation. While there's ongoing research into whether that preceding spacetime must include a singularity or not, it's not yet established whether our universe began from a singularity. In the vast book of our universe's story, we're still uncovering the earliest chapters. This brings to mind the topic of black holes, another fascinating area of study in our cosmos. In a universe that isn't expanding, any configuration of matter would eventually collapse down to a black hole. This is due to the fact that such a universe is unstable and must be expanding to avoid this black hole fate.
It's like that documentary I watched recently where they described black holes as hungry monsters of the universe, gobbling up everything in their path.
That's a great visualization. And funnily enough, black holes are also related to the concept of singularities. Let's take a Schwarzschild black hole, for example, where all mass collapses down to a single point, a singularity. Around this singularity is an event horizon, a sort of invisible boundary. Anything that crosses this event horizon cannot escape the gravitational pull of the black hole.
That reminds me of a game I played online recently where you had to try and escape from a black hole. It was impossible. No matter what I did, I ended up getting sucked back in.
That's a perfect way to understand the concept. Just like in your game, the flow of spacetime around a black hole acts like a moving walkway or waterfall, dragging everything into the singularity at the center. Outside the event horizon, however, other forces can often overcome the pull of gravity, allowing even infalling matter to escape. In the study of general relativity, we consider the behavior of test particles. These are theoretical concepts, where we imagine dropping something with any property we can think of, including mass, charge, spin, position, and speed, and we observe how it behaves in the spacetime.
Seems like a great way to understand the behavior of different properties in spacetime.
Exactly. Now, in a Schwarzschild spacetime, similar to how planets orbit the Sun, you can have stable orbits beyond the event horizon. But, once anything crosses the event horizon, it's drawn into the central singularity in a brief amount of time. There's no escaping it.
That sounds like a one-way ticket to, well, nowhere?
That's one way to look at it. This concept was actually a major contribution of Nobel laureate Roger Penrose to physics. He demonstrated how realistic matter, like a collapsing star, creates an event horizon and results in a future complete spacetime that ends in a singularity.
So, once an event horizon forms, it's just a quick trip to the central singularity?
That's correct. And at that singularity, we face an interesting situation. There's a finite, non-zero amount of mass or energy existing within a single point of infinitesimal size. Due to this, properties like density or temperature would theoretically blow up and go to infinity. It's a fascinating and complex concept, to say the least. So, at a singularity, we encounter what can only be described as pathological behaviors. It's where the laws of physics break down.
But isn't our universe not really described by idealized black holes?
That's a good point. In reality, black holes possess angular momentum or spin. In fact, all the realistic black holes we've observed are spinning at speeds that are quite relativistic, or a significant fraction of the speed of light.
So, does this change the way space behaves around the black hole?
Absolutely. This leads us to a different spacetime known as a Kerr spacetime, rather than a Schwarzschild spacetime. Here, the event horizon splits into an inner and outer layer. Also, there's a new region, called an ergosphere, where energy and mass can be extracted from just beyond the event horizon.
And what happens to the singularity?
Interestingly, the singularity changes in a Kerr spacetime. It's no longer a point but a one-dimensional object, like a circular ring. It's still a singularity, but now it's a line of infinite density. No matter how you look at it, we can't avoid the singularity with our current understanding of physics.
So, is it safe to say, once you're in the event horizon, it's a one-way trip to the singularity?
It seems so. One might imagine a compact collection of matter inside the event horizon that tries to resist further collapse, but this fails due to Einstein's relativity. No signal or force can move faster than the speed of light. So yes, it's a one-way trip to the singularity. So, all paths from inside the event horizon only lead further down and closer to the central singularity. You'd have to move faster than the speed of light to push backwards, and unless we throw out relativity altogether, there's no hope there.
That sounds pretty definitive. Are there any other theories that might change the outlook?
Well, there are two theoretical areas that might allow us to wriggle out of this fate. Firstly, we could appeal to an undiscovered theory that unifies gravitation and quantum theory, like a quantum theory of gravity.
Like finding a more complete theory that reconciles these two major branches of physics?
Precisely. And the second area is highly speculative, but mathematically plausible. It's the idea that a black hole could be a gateway to a newborn universe.
Wait, a black hole as a gateway to a new universe?
Yes, it's a fascinating idea. The energy of anything falling into a black hole could, in theory, re-emerge as part of a hot Big Bang in a newborn universe.
That's mind-blowing. But how likely is it?
Our only two realistic and best hopes for avoiding encountering a central singularity within every black hole are these: either quantum gravity will save us, which is a huge challenge in theoretical physics, or there's the possibility that falling into a black hole will result in a new universe on the other side. As long as we're stuck in our universe, and as long as the laws of general relativity hold, it appears that a singularity at the center of each black hole really is inevitable. To wrap it all up, it's important to remember that we're talking about the very boundaries of what we currently understand about our universe. Physics, as we know it today, breaks down at the singularity of a black hole. The immense gravity, the infinite density, these aren't conditions we can replicate or fully comprehend yet.
It's such an alien concept, but at the same time, it holds so much potential for uncovering new understanding about our universe.
Absolutely. And while we're left with a lot of questions, the pursuit of understanding these cosmic giants drives us forward. Whether it's the merging of quantum mechanics and general relativity into a grand unified theory, or the speculative yet fascinating idea of black holes birthing new universes, we continue our quest to unravel these cosmic mysteries.
I think that's what makes it so fascinating, the unknown and the limitless potential for discovery.
Indeed, the journey of discovery is just as important, if not more so, than the destination. These celestial puzzles, like black holes, continue to challenge our understanding and push the boundaries of our curiosity. So to sum it all up, we've journeyed through the concept of singularities, from the origin of our universe to the depths of black holes. We've explored the puzzles and mysteries they present, and looked at theories like cosmic inflation that attempt to answer these questions. We've also considered the tantalizing possibilities of a unifying theory of gravity and quantum mechanics, and the mind-blowing idea that black holes could birth new universes. But remember, in the face of these cosmic giants, we are but specks of stardust on a tiny planet, pondering the mysteries of the cosmos. Now, if that's not a humbling thought, I don't know what is.
Absolutely, it's been an incredible journey today. Thank you all for joining us on this cosmic adventure. If you've enjoyed today's episode, please give us a like, drop a comment, and share this with your friends. Let's continue exploring these mysteries together.
Yes, thank you all. We appreciate your curiosity and your company on this journey. Until next time, keep looking up and wondering. Goodbye, everyone.
Goodbye, and remember, the universe is full of curiosities, waiting to be discovered.
This fascinating exploration of singularities was sourced from an article titled Ask Ethan, Are Singularities Physically Real? On Big Think, written by Ethan Siegel and published on October 13, 2023. For those who want to dive deeper, you'll find the full URL in the video description. Now, I'm off.